Welcome back. And the first speaker of our afternoon session is Professor Vladimir Markovic from Tsinghua University. He will talk about the Caratheodory and the Kobayashi matrix on modular space of Riemann surfaces. Let's welcome.
Well, thank you for showing up to this plenary lecture. Given that you had a choice of plenary lectures, I'm glad you chose mine. All right. So I'll talk about a classical object in mathematics, by now very classical, which is essentially the Teichner space is the main object, and that feeds into mathematics in a number of ways. Today we discussed a geometric property of it from point of view of complex geometry, and so we will treat it in that sense. That aspect of it as a complex manifold is what interests us today, but of course other features will be important. For example, Teichner dynamics will come in, and I'll discuss how that feeds into the story. And well, let's start first with remind you of some definitions. So if you have a complex manifold, there is really not much you can do, but there is some beginning, there is a place to start. And essentially it was, essentially Kobayashi was the first one to define the notion of Schwarz-Peak metrics on complex manifolds. So, so Schwarz-Peak metric on a complex manifold X is any actually pseudometric D on X such that let's put it like this. If you look at all the maps from the hyperbolic plane into X, D of f of X, f of Y is not bigger than the hyperbolic metric between X and Y. And this holds for all holomorphic maps so essentially you look at X and you make it turn into a metric space with the property that the metric has basically is not expanded under holomorphic maps from the hyperbolic plane. And if you like, unit disk is a good model for the hyperbolic plane, and we might as well sometimes just think of it as the unit disk. And then you're mapping it into X by this map F. So you look at all the maps of the holomorphic maps of the unit disk into here, and the requirement on the metric is that it not increased under this map. And of course, manifold may have many such metrics. And in fact, they may be trivial, so that's why you really should think of it in pseudometrics. So, but the two metrics kind of at the opposite end of the spectrum are what makes this theory tick. And one is the Kobayashi metric. So the largest one is Kobayashi, called Kobayashi metric. And the smallest is the Caratheodory. So this can be defined formally. You cannot just say that you have to explain what we mean by largest and smallest. But your basic intuition is that simply comparing the distances of 2 points and maximizing them among all such metrics and then minimizing them essentially leads to these things. Formally, to do it, you need to do it infinitesimally and then integrate into a path metric, but that's essentially not going into these details. This is what happens. And just kind of, if you are, since I'm treating this more like a colloquial talk, maybe you can think of, and there are students. So in the case of some complex manifolds we know, like Riemann surfaces, essentially you can easily, on every Riemann surface, you can easily compute these metrics. So if the Riemann surface is the plane, complex plane, then the Kobayashi metric and both Caratheodory and Kobayashi metric trivial. They are zero. You can easily see that. And if the Riemann surface in question is, say, a hyperbolic Riemann surface, then the Kobayashi metric will always agree with the hyperbolic metric. And Caratheodory metric may be trivial in case of compact Riemann surfaces. Caratheodory metric will be trivial. So maybe I can say, right, maybe that is, okay, so I just want to say that this metric we will refer to dk, and this is dc. And by definition, dc of xy less or equal than dk of xy on x, xy are in x. Okay. So in a moment, I'll tell you more. In fact, maybe I should do it right now. Yes. So we are getting there, but let me first write. Actually, you can. There is a good formula for the Caratheodory metric, which I should give you. Is that the xy is that d h, but now it's going to be g of x, g of y. Sorry, I have too many d's. Better. And that's for g mapping x out of into the hyperbolic plane. So Kobayashi metric can be described similarly, but let me not do that because I'm mostly interested in this one. So these extremal metrics, the Kobayashi and Caratheodory, are essentially achieved. The Caratheodory metric is essentially supremum of distances in the hyperbolic plane for maps of the unit disk into the complex manifold, and the Caratheodory is the opposite. The Caratheodory metric is achieved as the supremum of the hyperbolic distance of images of 2 points, considering holomorphic maps out of the space into the unit disk or the hyperbolic plane. And that immediately tells you that if you don't have any bounded analytic holomorphic functions on your complex manifold, the Caratheodory metric is dead. Okay, and that also answers your question that, for example, if the Riemann surface is the unit disk, then obviously both Caratheodory metric and Kobayashi metric are equal to each other and to the hyperbolic metric. Okay, so that's the zero case, and everything else arises from there. So in fact, the beginning of this theory, more general for complex manifold, comes to this theorem of Kobayashi, who proved that on bounded symmetric spaces, the two metrics agree. This is the theorem of Kobayashi. And therefore, more generally, in fact, on Hermitian symmetric spaces, this is true. So complex Lie groups, when you look at the complex manifold underlying the complex Lie group and the quotients of it by the Borel groups, give you the spaces on which the two metrics agree. And this so the unit disk is, of course, an special case where the Lie group in question is PSL2R, PSL2C, I should say. And right. Anyway, the bottom line is that this theorem started the field, and it was then the question, and when you have a complex manifold, so we can simplify the problem. When you have a complex manifold the question is, what happens with these two metrics? And in particular, are they equal to each other? And what are they? So there are certainly reasons to ask that, and some of them I'll present here. We cannot say everything, but maybe in the context of tacular theory, I'll explain why that question is actually important. Okay. So there was after the Kobayashi's result, which was somewhere in the 50s or 60s, the next result of very notable result was one of Laszlo Lampert, who proved that the same is true. Where is this? So Lampert proved the same to be true on convex domains. It's a convex domain in Cn. So this is a generalization of the bounded symmetric domains. And on those domains, these two metrics agree as well. You might immediately ask, well, is that the extent of the complex manifolds on which the metrics agree? And the answer is no. Another important complex manifold called bisymmetrized disk is not convex, is known not to be biholomorphic to a convex domain, but on that domain, the two metrics also agree. So it is not a sole property of symmetric spaces. Yes, well, it doesn't have to be bounded. Yeah, he proved it for bounded, but actually recently, yeah, it's the same proof by approximation. You can prove it for any. Yeah, no, I can hear him. I don't have to worry about that. Okay. Okay, right. Sorry. No, it's not true in general for pseudo-convex domains. Yes, so there certainly are counterexamples to this. Yeah, in fact, it's unlikely, if you think of it, for a typical domain that's not convex, this would fail, even if it has smooth boundary. Yeah. Yeah. So it is therefore a delicate question, but the benefit is, in some sense, remarkable if the two metrics agree. That has some consequences in geometry. Okay. Okay. So now this is a background from in general. So the tacular space. So what's the tacular space? Tacular space is, as an object, is a basically a set of, as a set is a collection of marked complex structures on, say, a closed Riemann surface of genus G. So this is well, just to say topological surface genus G. You can add punctures if you like, but the bottom line is that the tacular space of this tacular space is a complex manifold which is realized as a bounded domain in C 3G minus 3. So bounded domain. This is, of course, a classical theorem of Baer's. And the Baer's embedding is really the mapping of the tacular space into this, the embedding into C 3G minus 3, which is then the dimension of the tacular space. So tacular space has all sorts of structures on it, and it feeds into various areas of mathematics, but as a complex manifold is a bounded domain. And in particular, it's a Stein manifold and everything else. Teichmuller space has the natural Teichmuller metric, something I will not exactly remind you of what it is, but it is it has other metrics like Weil-Peterson, but in particular, the Teichmuller metric is more natural from the point of view of complex structure in Teichmuller space. And so one of the founding results in Teichmuller theory and the most important theorems in Teichmuller theory, which had applications in important applications in tree manifold and everywhere else, is this Royden's theorem. So Hershey-Royden prove that the Kobayashi metric on the Teichmuller space is identical to the Teichmuller metric. And that is actually one of the theorems that kick-started this field in the 60s. The theorem is really easy to prove once you have the Teichmuller theorem, which is basically saying that every 2 points in the Teichmuller space lie on the unique geodesic with respect to the Teichmuller metric. In fact, they lie on the unique complex surface or a complex disk, which I'll tell you in a moment, called the Teichmuller disk. But nevertheless, this is a fundamental result. I mean, if you know something about three manifolds and you've heard of skinning map, which is used in the, which Thurston used in proof of hyperbolization, his hyperbolization theorem for Haken manifolds, then the fact that that skinning map had a fixed point, which was a key point in his proof, is the result of this fact. And the fact that the Teichmuller metric is being constructed under holomorphic maps between Teichmuller spaces. So if you map Teichmuller space to itself holomorphically, then the Teichmuller metric is not increasing under this map. And that's a fundamental fact in three-manifold topology. So the analytic side of Teichmuller theory, one question that remained basically since the 60s is what happens with a Caratheodory metric. And the question is whether Kobayashi equals Teichmuller equals Caratheodory. And this was the conjecture that was stated right after Royden's theorem. And today we want to, I want to tell you about this conjecture and explain some of its, well, give you the answer to it and explain some consequences of this. So, right. So from now on, obviously, we are focused on understanding Caratheodory metric on Teichmuller spaces. And as I told you, to understand Caratheodory metric on a complex manifold, and in particular on a Teichmuller space, you need to understand holomorphic maps out of the Teichmuller space. So we need to understand those objects. And to understand those objects, you need to be able to construct these holomorphic maps, and that, in fact, is not easy. And that is to understand them. Only the Teichmuller space is an abstract object, and you don't have really good coordinates for it. But some of them exist, and you have to somehow navigate this field to try to get some handle on these holomorphic maps. So let's see what classically is known about the Teichmuller space. So the tangent, so the space of holomorphic, if you have a Riemann surface, then you have the space of holomorphic quadratic differentials. And this is the space of these square forms. It's naturally identified to the cotangent space or to the Teichmuller space at the point X. So that's why this space is important. And the bottom line is that every element in here yields something called the Teichmuller disk, which is an isometric embedding of the hyperbolic plane into the Teichmuller space. Isometric embedding. So what this really means is that there is a lot of structure to the Teichmuller space. Like in symmetric spaces, you have, it's not just that you can define this metric, but you can say more. You know that every 2 points, P and Q, lie on a unique, they not only lie on a unique geodesic in the sense with respect to the Teichmuller metric, in fact, they live in the unique isometric image of the hyperbolic plane inside of the Teichmuller space, which is called the Teichmuller disk. So I'm not telling you here exactly because that would be perhaps too much today, but how these titular disks depend on the quadratic differential. You should think of it that this quadratic differential is kind of giving you the tangent direction of the titular disk at the given point. That indeed is what happens. But the theorem, and this is essentially the titular theorem, which started the titular theory in the 40s or in the 30s, is that every 2 points lie on unique titular disk of this. And that is what Freud then used to prove that the Caratheodory, that the Kobayashi and the titular maps metrics are the same, because this gives you these maps from the hyperbolic plane into the holomorphic and isometric maps into it. Okay, so now the question is, what happens with the Kobayashi metric and with the Caratheodory metric? And something nice happens here, is that if you assume that the Caratheodory metric at P and Q is equal to the titular metric at P and Q, then that is true for any pair of points in this titular disk. And in fact, it is true for a pair of points if and only if it's true for any pair of points in this titular disk. Okay? So therefore, the question about whether the Caratheodory metric equals to titular metric reduces to a question on each titular disk, each of these complex geodesic disks separately. So you have to ask the question, and not just for any pair of points. I mean, that in turn that is implied, but the question is, on which titular disks do these metrics agree? And that makes it nice. And so that you can ask these questions, well, how does that actually, and if at all, does this depend on this holomorphic quadratic differential? Okay. So you have this natural question, is to classify and characterize titular disks on which the two metrics agree. So, so this question was approached first time by Irving Krah and then by Kurt McMahon, who proved the first results. So they considered what's called as abelian titular disks. So these are the disks corresponding to, so quadratic differential is abelian if, in this case, if it has, so let me put it this way. Phi is abelian if all the zeros of phi are even order. This does not essentially mean that it's a square of an abelian differential, but it's very close to it. So let's just agree here that abelian means this. Okay, but in particular examples, and the most important examples are those quadratic differentials which arise as squares of one forms. Abelian, which is a holomorphic one form. One form on X. So if you take one form, square it, you get the quadratic differential. But more generally, you consider those which have even order zeros. And then, essentially what happens is that is this theorem that Krah and McMahon. I write Krah's name first because he proved it first and McMahon discovered it. Rediscovered it, right? That's how he says. So anyway, it's an important, beautiful result. It says that the Caratheodory, Kobayashi, and titular metrics agree on abelian disks. So if you have a disk, this whole disk, the metrics agree. Abelian in this weaker sense, yes. That's right. Say that again. Right, excellent question. So I didn't, because not that much time, but let me answer it. It's a theorem of Cliff Earl. Actually, so many people worked in this field, and Earl and Yao, ST, have proved in the 70s or 80s. Yao proved this in the 80s, and Cliff proved something early, that these are metrics. They proved that the Caratheodory metric is a metric comparable to the Teichmuller metric. But the question is, of course, is it equal? But it's certainly comparable. There are some open problems whether the comparability constants depend on the genus or not. I'm actually even not sure what the status of that is, but it was proved that they are metrics and comparable. So yes, of course, they are not trivial. We are not. Okay, so these disks, they agree. And in fact, how do they prove this? The proof is even more interesting than the theorem here, because they use the period mapping. The classical period map is being used here. So maybe I'll write it like this. You map the Teichmuller space into the Siegel upper half space. By the period map. Let me not write out the period map, but the point is that this is an embedding of the Teichmuller space into this symmetric space. This is a symmetric space based on the 2G square matrices of rank 2G, having some conditions. And this gives you, this is not just an embedding, it's of course a holomorphic embedding. And what they prove is that the abelian Teichmuller disks are mapped into complex geodesics in here. And then essentially by Kobayashi theorem, you know that the Caratheodory metric agrees with the Kobayashi metric on this symmetric space. And it is actually equal to the metric coming from the Lie group structure. So all the metrics are agreeing. And so basically going back to that original result of Kobayashi, here it's really true that these abelian disks are mapped to these guys. And that's the end. And that's in fact not hard to check once you are, it's a little bit of variational computation involved. Kurt McMahon proved much later, and in fact somewhat recently, that other Teichmuller disks are not mapped to complex geodesics. And that is actually only true for abelian disks. But the way you should really think of this is kind of an important point, because it really, in the end, it will lead to a natural conjecture as to what the Caratheodory metric of the Teichmuller space is. You know, in low-dimensional topology, always the idea is that the topology determines geometry. And there is a conjecture just like that here. In this time, complex geometry should be determined by topology. But the point is that this Siegel upper half space has a plenty of holomorphic maps out of it. So you can map holomorphically out of this space at will. And that, through this embedding, gives you many holomorphic maps out of it. In fact, you can use even this theorem just to show that the Caratheodory metric is a metric, because this is an embedding, which is a theorem of Torelli, classical result. Okay. So basically, from here on, Kra proved this in 1985, and Kurt wrote papers in the 90s or early 2000s. Yes, it was briefly.
There's an SL.
Yes. Yeah. So that will come. Yeah. Let's talk a little bit later. We'll discuss that. Yes, that's very important. The SL2R action will be important here. Yeah, we will see how that relates and what's the role of dynamics. And yeah, it will be answered. So believe me. Let me just formulate in some sense what the conjecture is. Classify all Teichmuller disk where the metric agrees. And in particular, one conjecture is that this is true if and only if it comes from this construction. Whether this is really the only case when that happens. In other words, when the holomorphic quadratic differential only has even order zeros. So that is a particularly natural conjecture to make. Okay. But this, I still haven't told you, we still don't know whether it's still possible, of course, that they are equal on all teichner disks. But as we will see soon, that's not the case. And that's why I'm formulating these conjectures really as something that is still a goal of the research in this area. So, well, let's actually get to it right away. So I was, of course, interested in this question since I was a graduate student from in the 90s. And I thought about it for about 20 years. And then I could prove this here, that these metrics are not equal on the teichner space of a five-punctured sphere, which is really the same as the torus with two punctures. This is the first non-trivial teichner space, which has complex dimension 2. And if I have time at the end, I might tell you just a couple of words as to what goes on here and how L-shaped polygons actually lead to these examples of teichner disks on which the metrics don't agree. It really comes from L-shaped polygons. But this is a complicated, it's a construction, and I might tell you in a moment more about it, but the consequence of this immediately is that the metrics differ on every teichner space. And that is because this guy embeds isometrically into here. So every teichner space has an isometric copy of this guy. And then by tautologically, you can show that if the Caratheodory metric is not Kobayashi metric on T05, then it cannot be in any space where you have an isometric embedding. And that is really the point. So this comes for free. And this is an example where if you disprove the theorem, you can do it in one case. Of course, if you wanted to prove something, you'd have to do it in every case. And since I'm at this, I can tell you that Dmitry Geckman, and Dmitry was my grad student, we proved actually this conjecture that we classify the teichner disks on which they agree, the two metrics, and verified that in fact it's true only for teichner disks with even order zeros in the case of T05. So we did prove the full classification in the simplest case. But of course, that does not extend automatically to any other teichner space, and that problem remains fully open to understand really on which teichner disks disagree. And there is another beautiful thing here, really. There is a different perspective that you can look, is that if this is like the teichner space, and this is the complex geodesic, in this case, the teichner geodesic, then the Caratheodory metric is equal to the teichner metric on this disk if and only if there is a holomorphic projection onto this teichner disk of the whole space. In other words, the space has to retract onto the disk. So is there a retraction from the teichner space onto teichner disk? Can you holomorphically retract? And you can, for the abelian disks, as shown by Cry and McMahon, and you cannot for some disk in T05, and therefore for some disk in the in any Teichner space. But it's still, you still want to describe the Teichner disks on which are holomorphic retracts of the Teichner space. That's the, so we're called peeling them, expanding the story. But this is really, in the end, the right way to think about it. So we started by some abstract metrics, Schwarzschild metrics. But in the end, it comes down to this question, to describe holomorphic retracts of the Teichner space. Okay. So let's now do a digression and briefly talk about a related problem. So the conjecture of Seal from the 80s as well. So Seal was considering with other people, basically the idea is to understand complex domains in the complex space with interesting group of automorphisms, and Teichner space is like that, and try to make a connection between, if you have a rich group of automorphisms, then you're either, say, a symmetric domain like the ball or a polydisk, or you must be very fractal. So they were trying to make a dichotomy in this sense. So it kind of, in more concrete terms, Teichner space is a bounded domain in the complex space of dimension 3G minus 3, and it has a rich group of automorphisms, which is, of course, isomorphic to the mapping class group. It's a discrete group acting on this bounded domain in Cn. And the question is here, can we actually realize so Bayes embedding gives you one map from the Teichner space into the complex space. But can you do it so that the image is convex? And for some reasons, which I'm not going to get into now, this was the conjecture of Seal, is that show that the Teichner space is not biholomorphic to a convex domain. Okay. So as I told you at the beginning of the lecture, Laszlo Lampert extended Kobayashi theorem to convex domains, and he showed that on convex domains, the Caratheodory and Kobayashi metrics agree. So now you put 2 and 2 together and observe that we can prove the Seal's conjecture, because Teichner space, you know that the two metrics don't agree in general. Therefore, it cannot be biholomorphic to a convex domain. So that's how I basically prove this conjecture of Seal. That's a byproduct of this story in complex geometry. Okay, so that was about Seal. But let's now kind of delve more into this story about the Teichner space. And yes, Bruce. So I think there is people work on that, and there are results. So far the results are all in negative direction. So this kicked off some direction of research into showing, well, it cannot be even locally convex, and it cannot have this kind of second fundamental form or whatever. But in the other direction, there are no results. There is any improvement on the Bayes so far. That's for sure. So I guess the real theorem would be, can you do any better than Bayes' embedding? And that would be an actual theorem. So far, I don't see that. But this was just on the other extreme. This conjecture of Seal was like saying, can we be convex? And even such a question is hard to answer here. I mean, you needed to do something kind of different, go really long way around to get to it. It wasn't done in any explicit way. What's quasi-convexity? There is pseudo-convexity here.
Quasi-convex, like
The tachylar space is quasi-convex. It's a pseudo-convex, as they say. So there it has some quasi-convexity properties. That is not enough in general for yes. So I don't know. The tachylar space already is pseudo-convex. This Bayes embedding gives you a pseudo-convex image. Yeah. So, but that's very broad. You can be fractal and pseudo-convex. So yeah. Of the Bayes embedding, it's it's known that it's not smooth in any. There is no smoothness, so it's kind of it's fractal. It's like a quasi-disk. It is, but it is in the terms of, in sense of, in complex analysis, in several variables, the notion of pseudo-convex domains does not exclude being fractal. That's just yeah. Okay. Oh yeah, that's different. Yeah. So I don't know the answer to that. Yeah. That's different. That's not what would be considering several variables. But yeah, if you are more geometric in that sense, then I don't know the answer. Maybe they proved it. I wasn't really following what these people were doing lately. Yeah. Yeah, I was more interested in this question, it's understanding on which disks this projects. To me, that sounds like a fundamental question. Okay, so let's talk more about that. So why is that kind of interesting question? How that connects with the rest of tachylar theory? And this is kind of and this also kind of explains how you can approach this conjecture of classifying these disks, tachylar disks, on which the two metrics agree. So here is the point. So here is the theorem. I'll state it as a theorem. It's going to be easier. Yeah. That dc is not dt on a random tachylar disk. So now it is useful to think of the type. You see, the tachylar space is the universal cover of the moduli space, which, although it's not compact, it's essentially like compact. It's finite area, and you can do dynamics on it. So the tachylar disks projects onto what we also call the tachylar disk in the moduli space. And now this moduli space, because being essentially compact, this tachylar disk cannot just go away. I mean, it's going to keep coming back by essential Poincaré principle of whatever recurrence. So and that applies here. So if you take a typical tachylar disk, its closure in the moduli space, and therefore will be all tachylar disks. So orbit closure under the SL2R action, which I'll mention in a moment, of a typical tachylar disk will be all tachylar disks. So therefore, on such a random disk, on which this closure is everything, the two metrics cannot agree. Because if they did agree, of course, they would then agree on every tachylar disk in the orbit closure. And we know that there is one on which they disagree, therefore they disagree on a random one. So beautifully, all of a sudden, we have this result that actually on a random disk they agree. On the other hand, they agree on a billion differentials, but that just makes us, that's of course not a random, that has a smaller dimension, but it makes a stratum of its own. So you have this nice stratum of a billion differentials, and on them they all agree. So that also makes sense from this dynamical point of view. Okay. So what was I talking about? So let's talk about the GL2R action. So GL2R acts naturally on holomorphic quadratic differentials, which is the cotangent bundle, and therefore it acts on every tachylar disk. So locally speaking, in local coordinates, tachylar disks are basically represented by tachylar maps, which are locally affine. So just the standard GL2R action as affine transformations yields this GL2R action on tachymere disks. That's all I'm going to say about it. Some of you know what I'm talking about. The others, you'll just have to learn. So the bottom line is that you have this group is acting not on the tachymere space, but it acts on its cotangent bundle. So you take a tangent or cotangent vector, and then there is an orbit, GL2R orbit of this vector. And orbits are exactly these tachymere disks, but orbit closures are a different story. So they might be and are typically much bigger than just the orbit. So the only, I guess, so the examples where the cases when the orbit and the orbit closures are the same, these are these Vij surfaces, or basically very rare tachymere curves. What do they call it? Right. But typically the orbit is much bigger. The orbit closure is much bigger than the orbit. And that actually is going to play a role here in this classification theory. So I already told you. So for a random disk, the GL2R or the closure of the orbit is everything. So that's what proves this previous theorem here. Okay.
Very special condition.
No. Well, there is the orbit and the orbit closure. So what's your question?
Orbit is dense. Like not all orbits are dense.
Yes, but the typical orbit is dense. Yeah, typical orbit is dense. Well, that was already used in this theorem, but that has much bigger legs. But you need much bigger tools. You need like to pull Skin's result and Wright's results. So we need to start we need some heavy machinery from this theory to continue to lift what we need to lift. Okay, so let's explain something about that. Now this is more special, but anyway. But before we get to that, let me explain to you why is that important and how that feeds into this story. So this has to do with the proof of this theorem is based on a criterion that I established for a tachymere disk to be a holomorphic retract. In other words, for a tachymere disk, so that the two metrics, all natural metrics agree on it. And since I don't have all that much time, I will not state to you this criterion in full, but let's draw some pictures. So whenever you have so holomorphic quadratic differential is an interesting object because it also, if you take its absolute value, it gives you the density of that corresponding density yields a metric on the Riemann surface, which is flat except at the zeros of this holomorphic quadratic differential, so you have negative charges. So we know by Gauss-Bonnet that there is the total curvature has to be negative, but so the metric is everywhere. The curvature is zero except at negative charges, where its curvature is focused and being negative. But what this essentially enables you to do is enables you to do Euclidean geometry on Riemann surfaces for every quadratic differential. And one thing you can do, and this essentially was done by Kurt Strebel, and then people continued, but the bottom line is that some quadratic differentials are more special than others, and we call them Strebel differential. And the Strebel differentials are those so that the Riemann surface is divided, X is divided into annuli, into horizontal annuli. So these annuli are, of course, glued along their boundaries to other annuli, and sometimes you have three prongs where the singularities will be on the boundary of these annuli, but on each annuli, the metric is regular Euclidean metric, and you actually have a flat annulus. So this is really true only for special quadratic differentials, but by theory of Mazur, Howie Mazur proved that these are dense among all quadratic differentials, which makes it certainly gives it significance. So it's not some rare occurrence. I mean, it is statistically rare, but geometrically not rare because it's dense. Okay. So essentially, my theory, what I developed is a criterion for these differentials. So for Teichmuller disks corresponding to stable differentials. Stable differentials. And essentially, what this is not exactly quite the criteria, but something like this. It says, if I'm lying a little, but not by much. If you have a stable differential with at least 2 cylinders, one cylinder is no good. But if you have a stable differential with 2 cylinders, at least 2 cylinders, with an even order 0 and an even order 0, then that's not a holomorphic retract. So that would be this criterion. So criterion, roughly speaking, the Teichmuller disks, stable differentials with at least 2 cylinders and even an odd order 0 is not a retract, is not a holomorphic retract. Okay, so essentially, I mean, certainly it's such, and I will show you in just a few minutes how L-shaped polygons give you examples of such stable differentials and Teichmuller disks with this property. So this is now a source for Teichmuller disks which are not retracts. But the question is, can we actually classify these guys? I mean, in some sense, the question really becomes, if I take a quadratic differential, I'm now interested in the whole orbit closure. And I come naturally to the question, is there such an object in its orbit closure? So can I say that orbit closures of holomorphic, of these Teichmuller disks contain Teichmuller disks corresponding to quadratic differentials that are stable and have at least 2 cylinders? And those who know Teichmuller dynamics, for some reason, completely for reasons that come from, this was actually a central problem. It's one of the central questions in Teichmuller dynamics, actually. So I'll say a word or two about that. So you really need so maybe just say a couple of words about that because it's important. So the first generation results were proved by Yair Minsky and Barak Weiss. So Minsky, Weiss, and Smiley Weiss. They proved that GL2R orbits closures of any holomorphic quadratic differential contains a stable one. But that's kind of essentially follows from general principles, dynamical principles. But of course here, and they were also interested for different reasons, you want to have a Teichmuller disk, not just that it's stable, but it has at least 2 cylinders. And that is like a super involved question. But so basically you have to combine all the big tools in the field, in particular Mizrahi asking result on classifying invariant measures. That's a big tool. And a bunch of other things, the fact that it's an affine manifold and whatnot. And then Alex Wright was actually Alex Wright. So he shows that orbit closure of Teichner disk with corresponding to phi with odd 0 contains Jenkins, contains, let's say, Strevel differential with 2 cylinders, or at least 2 cylinders. So they essentially did it. I asked them to do it. They just, but it was just not much. It was already published. There are some. So this is where this theory gets complicated, and I'm not really an expert. I even forget, but it's kind of complicated. There are many of these disks. There are fine details, but morally speaking, this is really the case. So if you have an odd 0, you will detect in the orbit closure Teichner disk that corresponds to a stable differential with at least 2 cylinders. So this is kind of how. So as I said, the criterion I gave you was proved really only for these low-dimensional Teichner spaces. So it's not really proved yet for all Teichner spaces. But if it's proved, which is expected, then you can use this result in full generality, and that would lead the classification of proof of this classification conjecture that which Teichner disks are retract, and basically those that only have even order zeros, which is the conjecture. Okay, so this is we used this, but we combined this already in low-dimensional Teichner spaces. This strategy works, but obviously there are things there that are simpler than in general, and probably more work needs to be done. So in a few minutes, let me just give you an example of this, how to construct. This is one and only example I'm going to give, but it really contains this whole story in it. So I've noticed a few years ago, lots of years ago, you go to airports, and then you see, what do you see at these airports? If you look like this, you see a L shape, but then it's really a pillow. So you take 2 copies of this polygon and sew them along the boundary, and you get this pillow, L-shaped pillow. So this is really what I want. So this L-shaped pillow is actually represents the Riemann sphere with, and the dizzy metric, the dizzy square metric on these 2 copies of the polygon glues very nicely, but there are problems at these corners. So these 5 corners are going to be the first order poles of the resulting quadratic differential, and this is going to be the 0 of this differential. Okay, so this L-shaped pillow is not just a pillow, it is the 5-punctured sphere with a holomorphic differential. But wait, it's not over. This holomorphic differential is stable, because what happens is that, so I'm now going to draw it as a pillow. Sorry. Okay, so this is one cylinder, and this is the other cylinder. You have 2 cylinders. So maybe I'll draw it one cylinder here, and the other cylinder here. And they are glued here. So the way you glue it, you first zip this and zip part of this. So you zip the part of this and glue it along this cylinder, and then you zip the bottom and the top, and there you are. But on this Riemann surface, you have two horizontal cylinders that are glued. And you can see the singularities appearing on the boundary of these cylinders, as I promised. Okay, so this is really an example. This 0 is of odd order. It's a first order 0. And actually, the computation was to show that Now, if you take the titular disk corresponding to this quadratic differential, that's where the metric exists. That's not a holomorphic retract. And this is kind of the blueprint for this theory that I believe exists in general. And in fact, it is this result that is used to classify holomorphic retracts in these low-dimensional titular spaces, because you can show that for any, so if you have an odd order 0, then essentially you have this guy in orbit closure. This is what you use titular dynamics to prove. Okay, I guess I'm out of time, so I should stop here. Thank you.
All right, so any questions or comment?
Yes.
So there's a Thurston boundary, and there's also some visual boundary kind of stuff. And there's this question about whether these titular disks, or you can extend to the boundary continuously. And for one cylinder stable differentials, it's actually, I think you can. And I'm just curious, like, how are you using 2 cylinders? So 2 cylinders, actually you can't. The extension to the bound.
You cannot do it.
Right.
Is that what you're saying?
Yeah. So.
Well, not in that way. So
You're not using bound Thurston
no,
boundary.
No.
But
it is, so what is
some
used.
conformal invariant.
Thurston boundary is not conformal. So
Right.
it does not correlate with the complex structure. And it's actually different than the Bayes boundary. So I'm not sure how that would fit into this story, but maybe. What goes on here is that I defined, and in a seminar lecture I would talk more about, I defined the notion of titular polydisks. Alex Wright defined this independently in his papers. He calls it cylindrical deformations. But the bottom line is that titular disk is an image of the hyperbolic plane, or the upper half plane, into the titular space, isometric. But the titular polydisk is an image of a polyplane, a product of hyperbolic planes into the titular space, whose diagonal is a titular disk. So when you have a stable differential with 2 or more, however many polygons or cylinders you have, you get a holomorphic image of a polyplane with that many factors into the titular space. I call that titular polydisk. And it is using this embedding that I prove this criterion. I analyze its boundary and whatnot. So it comes from that kind of construction. Yeah. But I should say that construction appears in titular dynamics independently, but the same construction. Yeah. It's called cylindrical deformations.
Okay, so because of the time, maybe if you have any further question, you can communicate with Professor Markovic in private. So let's thank the speaker again, and our second talk will be back in 7 minutes.